Okay, everyone, welcome to this particular lab that we have chosen to kind of showcase for you today. And this is going to be total organic carbon, also known as TOC. Woo-hoo! All right, so as far as TOC goes, folks, there are a couple of different versions. And I'm not going to really talk about these versions. I'm not going to talk about the, in-depth discussions of the lectures of the TOC instrument and how this process works. And the reason is because you get a lecture module on it. So we get to discuss this machine and how it works and how it does its job for, at least a week to a week and a half, if not maybe a smidge little bit longer, depending on how much I enjoy that lecture material. All right, well, the TOC is going to come to us in a couple of different versions. You'll learn about that. That's not the purpose of this lecture video, because this is actually designed for the laboratory experiment. It is not designed to give you the theory of the machine. That is coming from somewhere else. So we are using today a combustion model of TOC. And combustion is basically this concept that I take an organic, I add O2 to it, and I get CO2 and water every single time. And if I design a machine that focuses on the amount of CO2 that is produced, then this is going to be in relation to how much organic contamination that is present in the sample. That sample could have came from your tap water, from your toilet bowl water, from your filtered refrigerator, from the door. It could have came from anywhere, from the river, from a lake, from a stream, from mountain to mountain and shining sea. Oh, that's a song, isn't it? Okay, so we're going to take this water sample. We're going to bring it in, we're going to analyze it, and we're analyzing it for contamination. So this contamination is in direct relationship to how much CO2 that it can produce, because it undergoes a combustion reaction. And that CO2, if we have an eyeball of the machine that's constantly looking at everything that goes on in that instrument, absolutely it does. I've got the eyes on you. All right, so it's going to be an NDIR, and that detector is called a non-dispersive infrared detector. So it's going to be looking for CO2 as it gets generated. As that comes through the machine, it's got one job only. Don't screw it up, because that one job is what you should be doing. That is what you have been designed to do. You've got no other responsibilities other than watch for CO2. So that is going to be, in a nutshell, what's happening here with the machine as we use them. Now, all the little details, all the little pieces and parts, and how these things all combine together into one little beautiful story of how this machine works is coming up. So you're probably watching some of those videos right now. You're probably completing some of those assignments right now, or we're talking about it in lecture right now, if you've got lecture with me in person, face to face. All right, so it looks like this is a method. This method is 415.1. All right, another method I get to put on a resume. So method 160, blah, 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 blah. I know TDS, and I know TSS, and I know total residue. And now I can put on here, hey, I've done method 415 as well. It's total organic carbon. I've used the TOC analyzer. By the time that this lab activity is over, absolutely, you've used it. And it will not be the only time that you will use the TOC analyzer in our laboratory program. All right, next up is the title. So we talked about that. It says ore oxidation. The analyte is total organic carbon. The instrumentation, not available, because, that really depends on the manufacturer that you've got. It depends on what you're using, blah, 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 blah. Who did you order from? And ours is actually a Shimatsu instrument. So again, these are certain things that we are talking about in lecture, and these are certain things that you're going to see in the lecture videos if you're watching those. But for us, if you've not made it that far yet, then Shimatsu is going to be the manufacturer of choice with our TOC instrument. All right, so it says scope and application. This method includes the measurement of organic carbon in drinking, in surface and saline waters, saline salt, domestic and industrial waste, and exclusions are noted under the definitions and interferences. The method is most applicable to the measurement of organic carbon above a 1 milligram per liter. And again, milligram per liter is parts per million. That is what that unit represents. If you are in our CTC 150 course right now, and maybe you're taking the standards and solutions, that is a math-driven course. It's all the math, all the calculations that we constantly see in the program over and over and over and over and over. If you've not made it that far, don't sweat it. Don't get nervous, because it's kind of my job right now to tell you, hey, you're a new face. You joined the program. Now you kind of dumped into the river. Now you got to kind of swim. So milligram per liter is part per million. That is another way that we represent that value. So it looks like these are going to be great. Oxidation version, or the combustion version, is going to be great if we want a ppm that's greater than 1. If we want something less than 1, then there is another alternative to the TOC with this. There are different options that are available, different bells and whistles that you can get on your instruments, and some of these instruments are way more sensitive and they can go lower. But the way that 415 is made, it says it's most applicable to anything that has a 1 ppm or higher TOC with us. Now, our instrument can go lower, and we're going to report those values. We're going to look at them. We're going to talk about them. We're going to build calibration curves. But for the most part, we do actually see numbers that are going to be greater than a 1. And the only thing that we see something low on are things like our deionized water and distilled water. Those types of things, of course, they're going to be lower than 1 because, you know, they should be clean sources of water that we are using in our laboratory spaces. But most of the time, our drinking water and anything that we bring in as a sample to run, they will be over a 1 ppm for us. Summary of method, it says organic carbon in a sample is converted to carbon dioxide. Oh, Tracy already told you that story. By catalytic combustion, that sounds fancy, of a wet chemical oxidation. The CO2 formed can be measured directly by, oh look, Tracy told me this too, an infrared detector, or converted to methane and measured by a flame ionization detector. The amount of CO2 or CH4 methane is directly proportional to the concentration of the material that's in the sample. All right, so what this means is that I've just told you the entire story and you didn't believe me. Why didn't you believe me? I just told you exactly what was going to go on, and sure enough, that's what the summary is basically trying to tell us. See, I don't lie to you all the time. Next up are definitions, and it gives me a little section, and it talks about some certain terms, some things that I need to be aware of. Guess what we're going to do? We're going to fast forward through that. Section 4 is the sample handling and preservation. So if I collect these samples, how should I collect them? If I can't run them immediately, how should I preserve them? So do I need to add something to it? Do they need to go in the freezer? Do they need to go into the refrigerator? Or can they stay out on my lab shelf for 6 months until I get to them, right? So that's what Section 4 is all about. And if I look in Section 4, on step 4.3, it says, in instances where analysis cannot be performed within 2 hours from the time of the sampling, you need to acidify your sample to less than a 2 pH, and you need to use HCl or H2SO4 in order to do that. So I'm going to tell you something right up front. I'm going to go, I don't like to use HCl. And the reason is because it is a halogenated type of compound here, right? I see chlorine that is there. And chlorines and bromines and iodines, those halogens, they cause me a problem. And those problems are going to happen in the scrubbers of the instrument that we have. So the scrubber's job is to remove all of those halogens so that they do not reach the detector. And I just don't like acidifying with a halogen if halogens should not be there in the first place. So if I get a choice, and I do in this method, then I'm going to choose something else to go with just because I know in my mind how that instrument is supposed to operate. If I start acidifying everything with HCl's, my halogen scrubbers begin to go bad, and then I'm going to have to replace those. And listen, it is not hard to replace the scrubber. Absolutely not. It's very easy. Anybody can be trained to do it in a couple of minutes. components. The problem is the money. So I don't want to keep forking out cash in order to keep switching out scrubbers, because we are adding HCl, which includes a halogen, which is a thing that cannot reach the detector, which is something that's got to go through the scrubber in our machine. So absolutely, if I get the choice, that's what I'm going to do. Also, 4.2 up above, it says, because of the possibility of oxidation, of bacterial decomposition of some components in the aqueous samples, ooh, listen to me, I'm so smart, the lapse of time between collection of samples and start of analysis should be kept to a minimum. Also, samples should be kept cool, 4 degrees Celsius, and protected from sunlight and atmospheric oxygen. What this means is that if I was going out and I was collecting these samples in the field, I would take my containers and I would fill that container to the top. By filling it to the top, I'm kind of pushing out all of the air that might get trapped into the bottle as I collect them. In addition to that, when I do collect them, I'm going to probably collect them in some type of bottle that prevents sunlight directly from hitting it. So I probably don't want to be collecting them in clear glass bottles. We've got amber bottles that would work, maybe some opaque bottles that would be okay. When I begin to collect them and when I begin to transport them, I probably don't just need to leave them wide open, so I'll probably need to keep them in some type of container, and that container is probably going to be a cooler because it tells me 4 degrees Celsius. That is the temperature of your refrigerator, not your freezer, because this is Celsius and not Fahrenheit. So 4 degrees Celsius is refrigerator temperature. All right, so that gives me some ideas now. If I go out and collect them, dark bottles, fill it to the top, put a lid on it, put it in a chiller, put it in a cooler, and then transport it back to the lab. When the lab gets it, they're going to take this container, and if they cannot get to it within around 2 hours, they're going to try to acidify it, and they're going to acidify it using preferably H2SO4 with us, or if you're crazy and you don't know what you're doing, HCl can also be used as well. Next up is the interferences, and guess what we're going to do? We're going to skip through the interferences. These are things for the SOP. So if I write an SOP for you, I'm going to say, listen, there's some things here that can interfere with the signal. Bicarbonate and carbonate can be one of those. You know, think of like baking soda, right? So we don't want that presence. We want to make sure that that presence does not interfere with our signals. Section 6 is apparatus, and it's just like, hey, just use something that works. That's what Section 6 is telling us. So it says a number of companies manufacture systems for measuring carbonaceous material in liquid samples. Ooh, say that out loud. Say it 2 or 3 times. Make your mouth feel happy. Considerations should be made as to the types of samples to be analyzed, the expected concentration range, and forms of carbon to be measured. So yet again, there are different versions of a TOC analyzer that are out there, and this is basically telling you, listen, for your job, the way that you've got to do the test, the way that your client wants your lab to report these values, you want to make sure that you have an appropriate instrument in order to do that type of thing. So if you do, then great, but you got to know something about the types of samples that you're running. Do you want to go super low? Because if so, the machine that we have in our lab probably is not going to go that low. But if you're going to be running samples that have higher than 1 ppm, then absolutely a machine like ours can be used, and a machine like ours is going to be commonly found in laboratory settings. So I don't want you to feel like you've been gypped, because you've not been gypped, because quite honestly, a lot of bachelor's degree candidates have no training on TOC. They've never seen a machine. They don't even know what it is. And then master's degree candidates are the same way. They probably have never came in contact with the instrument. They don't know how it works. They don't know how to run samples on it. So you are not being gypped at all. What's going on is that you are being given training that real world wants. So hello, we feature a piece of instrumentation and a method that is applicable to the job. Go figure. Isn't that what education is supposed to be about anyway? Why do I want to go study big lectures and theories and be like, oh, look at me, I'm studying the blah, 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 blah. Nobody cares, because that's not real world. All right, section 7 is reagents, and reagents is going to tell me, hey, these are things that you need to use. 7.1 is distilled water, and the reason we use distilled water is to make sure that it is super clean. And distilled water is going to be one of the cleanest water sources that we can get in a laboratory. So what we need to do, we need to make sure that this water is clean, this water does not carry contamination, and ours will carry a little bit. I'll go ahead and break that secret to you. And it says carbon dioxide free double distilled water is recommended. The reason is because carbon dioxide free, oh no! Carbon dioxide is CO2. If CO2 is in the water sample, then CO2 can be used, and CO2 is contaminating everything. And the whole purpose of this is to measure the CO2 that comes out of the back end of the machine. So if CO2 is there, it's going to be present. It's going to mess my results. And now I've got a problem if I'm not very careful. So that is why it specifically says carbon dioxide free water. All right. Okay. Then it says ion exchange waters are not recommended because of the possibilities of contamination with organic materials from the resins. This is how our deionized water works. So deionized water does not get boiled. It does not recondense or condense. It does not get collected. We are not removing any type of organic material at all. We are simply removing the ions. And an ion is something that is positive or something that is negative. So we are removing those things from the water sample. So for instance, your tap water at home has things like calcium, so Ca+2, and magnesium. It's got that as well. And we are trying to remove those things to clean the water up a little bit. Absolutely, that's what we're trying to do. All right, so with that said, and that magnesium also, by the way, carries a charge. All right, so we need to get rid of those. We can do that. We do that very easily through our ion exchange tanks. And that's the water sample that you will find in those faucets and those sprayers that's in our laboratory area. As of currently, we do not have a proper distillery. We are not using distilled water. Distilled water is way cleaner than deionized water, according to the definition, and that's because we are getting rid of those organics that might be present in that water sample. Now, there's different water sources that are out there. There's different kind of purposes for each one of them, but for today, ion exchange is the only thing that we're going to refer to. I will say, though, we are in the motion, and by the time that you take the course, we have ordered a ultra filtration system that will basically help us get to that moment. Not a full like distilled water type of environment or instrument that we're using, but folks, this is going to be super clean water. Almost not quite pharmaceutical grade water, but it gets us really close to that point for sure. In 7.2 it says potassium hydrogen phthalate. The potassium hydrogen phthalate, it tells me how to make it. So I can order this or I can make this. This is going to be our first standard that we abbreviate as STD. And this is our standard stock. So this is something that I have ordered. Maybe it has been shipped to us. It has been made by another third party. We get a little certificate and it says, we tested it and this is what our number is. Here you go. All right. That saves you some work. Well, the great thing with academics is that we don't have to double check it. So we just assume that it is 1,000 in the bottle. And that 1,000 is 1,000 ppm. So if you look at this, it's milligram of carbon per liter. So milligram per liter is ppm. All right, so that is not an N. It is an M, Tracy. Make sure that your chicken scratch actually is legible. That is one of the violations of a quality lab environment. Make sure people can read it. Okay, so ppm, there we go. All right, so milligram per liter, parts per million. This is what we're going to make. Okay, so it tells me measure out 0.2128 grams of potassium hydrogen phthalate in distilled water and dilute it to 100 mils. All right, so the problem here is that this is way too strong. We cannot be running 1,000 ppms on our machine. We shouldn't, at least, because that is nowhere near what our samples are going to be reading that we bring in. At least I hope not. So this is going to have to be diluted down, and that's what 7.3 is going to say. Potassium hydrogen phthalate. Prepare standard solutions from the stock by dilution with distilled water. So this is me making weaker solutions that are going to be more appropriate to run on our machine according to the types of samples that we are running on our instrument. So we start somewhere, and that is with our original standard that we've made in 7.2, and then 7.3 says now weaken them down. So again, my SOP is going to somewhat tell me that. It's going to kind of walk me through how to weaken these down, what measurements should I be using, how should I be pipetting, how should I be taking them to the line on the volumetric flask. But I've got news for you. And that news is that 7.3, it's actually going to be done by our TOC machine. I mean, come on, folks. We got technology. Technology is part of our name. So why not use the technology to do the job for us? If my machine can take my standard, and if it can take the standard and weaken something down and make a series of standards itself, then that's exactly what I'm going to do. I'm going to let the machine do it. And you're going to see that take place in our laboratory by the time that we get there. So this is going to be more than a one-day event. And on the second day is typically the day that I show you the instrument. How does it work? What's going to go on? And then I'm going to walk you through the steps of how to enter your information into the batch, and I'm going to show you the steps of how to get the machine to make the standards for you. So very, very important. That's what we're going to do. And, you know, great job. Great job, Shimatsu. Great job. You made my life a little bit easier. The problem, though, is that when you make the 1000 ppm up here at the top, this is still way too strong for that machine to use to make the standards with. So we're still going to do one dilution, and that one dilution, we're going to go down to a 50 part per million. When we go to a 50 part per million, then that's great. That's what we need to do. And that is what the machine is going to be using to make the rest of the standards with. All right. So there is going to be a little blurb in your directions that will tell you now that you've made the 1000, dilute it down. And when you dilute it down, that is what you're going to be using in the instrument to make your other standards with. All right. Next up is 7.4, the carbonate by carbonate mix. We're actually going to skip this. We're not running that at all. 7.5, carbonate by carbonate. Well, it's a series of calibration curves and diluted samples. We're going to get rid of that as well. And then 7.6 is a blank, and it's used the same distilled water that you have used for all of the other things that you have prepped. So we need a few blanks in here as well. So absolutely, there are some ideas of some of the samples that we need to kind of prepare and get ready for the auto sampler of my machine. Section 8 says procedure, and it says follow the instrument manufacturer instructions for calibration, procedure, and calculations. That's because they have no clue what you're using, right? Shimatsu is going to operate a little different than some of the other manufacturers that are out there. Again, we have a Shimatsu. We give you procedures of how to use that Shimatsu system, and that's what we're going to follow. So they have no clue, and they're giving this as an open-ended kind of overall general statement, so that way this is the purpose of the SOP. Go figure, I learned that in Module 3. I know that this is the method and this is where it originates, and now the company will take that method and a company will provide me with an SOP, and that SOP will have that information in it. That's why we have to modify it. That's why we are required to do that. So that way you know how to use our machine that we have in-house. All of these stars are aligning. How beautiful is it going to be? 8.2 for calibration of the instrument. It's recommended that a series of standards encompassing the expected concentration range of the samples should be used. So yet again, this is you, and you know something about the samples, and you know the window of the concentrations that it will fall between. So you want to make sure that the calibration standards are including those typical values. In other words, what this means is that let's say I make a standard calibration curve that goes from 1 part per million to 25 part per million. Okay, it looks wonderful. It looks great. my regression line is like perfect because I am so good. And then if I run samples and my samples fall below a 1, or if my samples go above a 25, then I really should not be reporting those, not with the exact numbers that the machine gives me, because it's only been calibrated in that range. It's only been calibrated between 1 and 25, nothing less and nothing more. So I cannot guarantee what those values are if it goes below a 1 or if it goes above a 25. I just simply do not know. I have no clue. So the only way to fix it is to dilute the samples down and rerun them to get them fit in that window, or I can expand my calibration window. If I can go maybe up to 50 and still feel good about it and get a great regression line and it's all linear and it's textbook perfect, then absolutely, let's expand my window so I can capture those higher level ppms that we have in our laboratory that we need to test, we need to analyze, and we need to report. That is a very important thing for calibration curves. And I think it's something that some people just are completely oblivious to. Your calibration curve sets the limits. We talked about this in Module 3 a little bit. You cannot go below or above those limits. If you do have samples that go below or above, you got to do something to them. You got to expand the calibration window. You got to dilute the samples, make them more concentrated, do something to them in some form or fashion in order to get to fit that range. Otherwise, we should not actually be recording legit numbers that show up on that report. We got to get creative. Number 9 says precision and accuracy. So it gives me a little idea about how good this process is and maybe how the precision is going to be with typical instrumentation and typical methods that I would see here in a typical laboratory environment. All right. So this is going to be the first kind of part of the method. This is where this video is going to stop. In the next one, we're going to take a look at more of the quality control tables that come along with method 415.1. We'll talk about these, what's there, what should be there at least, how should I handle these samples, and then we'll finally talk about the data sheets that we need to fill out. Welcome to the world of TOC. Here's part 1 of others. So you're not done. You've got nothing else to do. I know that you enjoy me talking crazy. So come back and take another gabble and listen and make fun of me even more.